Yes, so I am audible. So hello everyone. I am again back with another video after a long break. So what we are doing, we were discussing at Code Educational TP contest problems, and we have done up to in problem D knapsack 1. So today we are starting with knapsack 2. So without wasting much time, let's get started with the problem. So in this problem, there are n items numbered from 1 to n, and for each item I from 1 to n. Each item is having some weight and some value. The problem statement is similar to knapsack 1, where we are having a bag whose maximum capacity is capital W, and what we have to do is we have to maximize the sum of values which we will be taking up, so that the total weight which we are taking up is less than equal to capital W, right? So this is the same problem statement as knapsack 1. So these are the constraints. So let's go step by step. So the first step is identify the form. So this is form 1 problem. First step is now over. Second step is defining state. So let's define a DP state as DP of index comma W left, which is storing the maximum value that I can get in this range, such that W left is the weight that can be picked in the next part from this to this, right? So this is how we can define the state. Third step is define transition. Okay, so dp of index comma w is, so there are two choices at each state. We can either take this item or we can reject this item. Not taking, in case of not taking, the w left will be remain same and index will be incremented. So the if I am not taking, it is same as dp of index plus 1 comma w left, right? If I am taking, so I have to add the contribution of this current item to my answer, right? And weight left will be decremented by the weight of this current index. So let's now calculate the space and time complexity. So the number of states for this kind of dp is number of indexes into the total weight that I can left. So indexes are up to 100 and weight value is up to 10 to the power 9. Okay. So number of states is itself 10 to the power 11 and number of transition is 2. So applying after applying the formula for time complexity as the number of states into 1 plus number of transitions. So I will be getting time complexity as 10 to the power 11, which will definitely give me TLE. So we can't code this particular DP state. So let's see how we can change this problem. So in this type of problems where we can't in general store the variables in DP states because of constraint, we can use a concept known as state rotation. As the name suggests, we will be rotating the state. As I have already discussed in previous videos, that whatever is asked in the problem is like we store the particular result as the result of DP state, whatever is asked in the problem. Whereas we keep constraints and levels inside our DP state, right? But in this problem, is in this type of problem where we can't do as these type of things because of constraints, we will be storing the required result inside the DP state. Let's see how we can do this type of DP state. So this is the trick which we call as state rotation, because we are rotating state about the desired result. So let's uh, create a new DP state as DP of index comma v left. We have included the value inside DP state, and this is storing the minimum weight that I can have in this range index to last index, such that v left is the value that can be picked. Are you getting the difference? In actual problem, what we have to do is we have to maximize the value, keeping this in mind so that the total weight taken is less than equal to w. So if I am considering the state rotation, if I'm consider if I am storing the result as in the form of W, so it will be the minimum weight that I can pick, so that the um, value is maximum, something like that. That's why I formulated the DP state like this: DP of index comma V left as the minimum weight I can have. And for this V left, what I can do, I can iterate from the maximum value, that is 10 to the power 5, to the 0. So the first value, so the largest value which for which the minimum weight is less than equal to the capital W, it will be my answer, right? So let's see its transition: DP of non-take or take, right? So if I am not taking, nothing will happen. If I am taking, I have to take the contribution of that state as W of weight, and dp of index plus 1, v left will be decremented by v of index, right? And what we have to do is we have to take minimum of both of these states. So the time complexity for this type of dp state is, index is number of index, whereas the v can be up to 10 to the power 5, so the number of states are 10 to the power 7, and transitions are 2. So the overall time complexity will be 10 to the power 7, big of 10 to the power 7, which will not be give me TLE. So we can iterate for values from going from 10 to the power 5 to 10 to 0, and the first value for which the dp state like this, dp of 0 comma that value, is storing the minimum weight which I can pick, which is less than equal to this capital W. This value will be my answer, right? So let's quickly see its code. I've already coded this solution. This is the problem. So the input format is, we are taking n and w as input first, and then these. Okay, I have already created the vector weight value taken as input, and I have created 2D dp, dp of size n cross 10 to the power 5. This is the recursive function which I have implemented. So again, similar implementation: pruning, base case, cache check, compute. So in pruning case, where index goes n plus 1, that means I've already like considered the whole of array, and v left is considered in base case. So if uh, pruning I will discuss later. So if v left is 0, that means there is I can't pick more values. So the minimum in this type of case, the minimum weight that I can pick now will be 0. So this is just a cache check. Compute. Let's discuss the compute part. I have initialized the answer variable with int min, or you can say long min. This is not take case. And if v left minus v of index is greater than or equal to 0, that means I can pick this particular index. So I have taken that transition also into consideration. So answer equals to minimum of answer comma w index plus recursion of index plus 1, v left minus this v index. That's how we can implement this dp. And after implementing the recursive function, what I have to do is what I need to do is I need to have the maximum value for which the minimum weight is less than equal to W, right? So V left, I will iterate V left from 10 to the power 5 to 0, and the first V left for which this recursive call 0 comma V left is less than equal to capital W, this will be my answer, and I will output this. Let's quickly check for some of the sample inputs. Yeah, uh, is giving me 90 as output, and 90 is the correct output, right? Let's check for second input. It's 10. Yeah, it's correct. Let's check for third. 17. Right. Let's quickly submit this code now. Let's see if it runs or not properly. Yeah, it got accepted. So that's all for today's video. Let's quickly summarize the whole idea of this state rotation. So why the concept state rotation comes came into consideration? Because if this was the let's say if this was the normal knapsack problem, what we have done in previous knapsack problem, we have created a DP state as it is, yeah, DP of index comma weight taken, which will be storing the max value that I can pick in this section starting from index up to n minus 1th index, such that the weight taken has been already considered, right? So that's how I have created DP state in knapsack 1. But in this case, in knapsack 2, I can't create DP state like that, because if I am keeping this W inside my DP state, the number of states will go up to 10 to the power 11, which will definitely give me TLU. So in this type of cases, we generally rotate our states, right? We keep the desired result inside our DP state, and uh, we keep constraints as a desired result. We just swap those. So I have created a new DP state as DP of index comma v left, which will be storing the minimum weight that I can have in range index to last index, such that I have I can only pick up to weight left, right? This was a transition, and the time complexity for this code is up to big O of 10 to the power 7. So plus big O of 10 to the power 5, which will be up to big O of 10 to the power 7 only. And space complexity will be, as dp is 10 to the power 7 only, so space complexity is also big O of 10 to the power 7. So that's all about the problem, knapsack 2. After that, we will be discussing this problem, LCS. Okay, so that's all for today's video. Thanks for watching. Bye bye.